now we will summarize this topic of the waveform analysis. First, what we had looked at, that is the signal length, that we need to keep in mind that signal length is not the duration of the signal, but what we are looking at, that is the spread of the energy of the signal. So, if we go back to the formula of that signal length, that will help us to remember that it is the ratio of the energies. In the numerator we have a weighting function, that W n, that is giving us actually the change, and the W n is a non decreasing function. The simplest form of it could be that it is monotonically increasing. Okay. So, in that case, that what we are interested to get, that the signal distribution is how far from the origin. Okay. If the signal is located near the origin, the signal length would be small. If it is away from the origin, then that value would be more, even for the same amount of energy, and to make sure that we have actually used that estimate of the energy of the whole signal in the denominator. Okay. So, that was that notion, and this has been used for many things like ECG signal in particular, starting from the P wave, that it has been done, and most of the energy is concentrated in the QRS complex. So, to get actually that how much energy is there in the QRS, that in case of ectopic beat and PVC, we know the QRS becomes wider, the ST segment that gets elevated. So, all these things can be actually captured in that, though that there is not much change in that spectrum of that PVC signal and compared to the normal that spectrum of the signal. Okay. But signal length is able to actually get that, because it not only depends on the magnitude of the spectra, but the phase of the spectra. So, that Murthy and Rangaraj suggested a technique that they let us look at that part from P to T wave, and what they have suggested to use actually MCP, and using that they have conducted an experiment where with the help of linear classifier they have shown that if we have taken the minimum phase correspondent, that we can get better classification here compared to that the signal, if we take the signal length, which also somewhat gives the separation. Now, here another part comes in that way, that is minimum phase correspondent or minimum phase counterpart, that MPC, that if we look at that MPC formula, that here we have given that if we compute that autocorrelation of the signal, and if we go to the septal domain, then we can, using this formula, we can get that minimum phase correspondent of that signal, but we need to keep in mind it is in the actually complex spectrum of the signal. So, we should look back that what was that how to get from the complex spectrum to that time domain signal. For that we need to remember that homomorphic deconvolution steps. Actually, the spectrum, when you look at it, is here that we have computed. So, after that the steps which are necessary, that we need to take, and even for computing that from the autocorrelation we need to come through this forward path. So, with that we have computed that the minimum phase correspondent, and at the end of it that we get the corresponding the time domain signal, which is of importance. And what is so important here, that when we take the minimum phase counterpart, we make sure that the starting point becomes actually the same for all the signals. Otherwise, what will happen, that where we have taken the P wave, by a small error of that, will change the phase of that signal, and because signal length is very much dependent on the phase, it will be disturbed by that actually noise, and that is why we get, when we take the minimum phase correspondent, we get much better result compared to that the original signal. Okay. And then we have gone for that ECG wavelet analysis. The simplest form of it, if we take that here is the baseline say, and we are taking that P wave followed by the QRS complex, then T wave. We are actually interested in that, this is the duration, then this gives us the height, then the midpoint of the height we get, and what is the difference of it from that baseline, that gives us some actually way that how to describe that QRS complex or the properties of it. So, that was one of the suggestion for ECG waveform analysis. Then we have gone for envelope detection. So, first we have gone for synchronous demodulation, where we have assumed that we know that carrier signal, and not only the carrier signal frequency, but the phase of it. So, it is a bit synthetic kind of situation which will not get in practice. What we will get actually, that we get the signal there. So, I think in practice asynchronous demodulation would be more useful, and both the synchronous and asynchronous, they are assuming that it is a monotone kind of signal, only one strong actually that frequency is present and there is small variation around it, but in real life the signal could have actually multiple modes in the spectrum, that means multiple tones could be there. So, for that we should go for the complex demodulation, where we target each of the band one at a time and take that the peak of that as the carrier frequency or the central frequency of that, and find out the corresponding modulating signal, the amplitude as well as phase, and we repeat that till all the prominent peaks are actually represented, and thereby we get the full description of the signal. Now, another technique is the envelogram, and that there are different motivation for that. If we look at all these signal techniques, that synchronous averaging, asynchronous averaging, complex demodulation, we are using a filter, low pass filter is used, and because of the low pass filter operation, low pass filtering operation, we need couple of samples to actually to do that filtering operation, and that depends on how many points would be required, that depends on that what kind of filter we are using, what is the length of that filter. Now, that essentially means that we never get the instantaneous energy or the envelope of the signal. Now, if we are very particular about the time, we want the time resolution, then we need to think in a different way, and from that point of view the envelogram was suggested, where the Hilbert transform of the signal was computed, and that added up with the original signal, that the complex combination of that gives rise to analytic signal, and the amplitude of the analytic signal provides the envelope of that real signal. So, using that fact we could get the envelogram, but still the problem remains that how to get that Hilbert transform so easily. Now, to address that, we looked into the fact that if we go for the analytic signal, that only that real part of the frequency we have the energy, that negative part of the frequency, that energy should be 0. So, using that observation, we modified that spectra of the signal in that way, in the frequency domain. So, this energy actually that we took the DFT and manipulated the spectra to get the spectra of the analytic signal, and by the inverse DFT we got actually the envelope. Now, while we could get the envelope in that way, which is accurate in that way, the penalty what we have paid, that because of the Fourier transform or DFT, we have to wait to get some number of signals, because the resolution of the Fourier transform of DFT that depends on the number of that points involved in it. So, essentially it becomes a block processing algorithm, unlike the previous techniques. So, it becomes another offline technique. Okay. So, that is the trade off. Now, let us look at the other set of actually that waveform analysis techniques. Here we have the techniques, the analysis of activity. Primarily they are concentrating on the frequency part of it, most of them, except for the RMS value. RMS is looking at the energy of that signal and how they are varying with time. So, we can say the amount of information and the quality of information is very similar to the envelope detection algorithm. So, it can also give us some kind of envelope, but the definition of the envelope changes in this case, and it has an interpretation in terms of energy that gives it the strength of existence. Next, all the other actually that the techniques, the zero crossing and the turns count, both of them they are actually dependent on the change in the frequency. We know the signals like EMG, the activity becomes more when we are trying to lift actually that more weight or trying to exert more force. That if there is murmur in the PCG wave, again there is change in frequency, and that is actually captured by the simple algorithms like zero crossing, which gives the basic notion of change in frequency or the frequency of the signal. Same thing we can get in the turns count. The advantage of the turns count is that zero crossing was affected by the DC baseline. If we think of a arbitrary signal, that arbitrary variation of the signal, that then that whatever the baseline will take, that may determine that how many actually crossings are happening. If we take the baseline here, the results would be different. If we move that DC baseline, the results will change. So, either we need to remove that DC bias, that is one way to take care of that, or we can go for the turns count, okay, which is not again affected by the DC bias. But again for the turns count, that is getting affected by the high frequency noise, and to take care of that, what the people have done, that as the high frequency noise gives a small kink in the signal everywhere. So, they have told that peaks which are only prominent or having actually that samples in both the sides which are lower or higher than that point, that means if this is a peak, that before other turn so many points should be there, and these length should be, that this magnitude of this change in between, they should be a minimum number, only then I would take that as a turn. And for that example they have taken, it is 100 microvolt, but this value is dependent on that signal and the amplification. Okay. So, you need to select this value carefully, which would make it immune to that the noise corruption, but at the same time it should be sufficient to get the variation of the signal. So, it should not be too high in that. So, at the end of that we have gone for the technique called form factor, and form factor is really looking at that how the signal energy is changing and what is the shape of it. And for that purpose we can say that as a form factor is 1 for our that sinusoid signal. So, sinusoid is the simplest form of actually oscillation, and that is taken as a reference that our signal is how different from the sinusoid, that is what is measured by the form factor, and that also depicts the shape in a very concise way. So, with that we complete this chapter. Thank you.